Hello everyone, welcome to the presentation on Synchronous FIFO design and verification. In this video, we will break down what is actually FIFO, how synchronous FIFOs work, how can we design and verify them using Verilog. Don't worry if you are a beginner, we will start with a real life analogy to understand the concept in a simple way. So let's begin. So what is FIFO? FIFO stands for first in, first out. Think of it like a waiting room for interviews. Let's say a few people are already waiting in line to give their interview and you enter next. The person who came first should be called first and the person who came after waits their turn. This is exactly how FIFOs work. The data that enter first will be read out first. Through analogy, we can understand what FIFO is. So now we will discuss about the types of FIFO. There are two types of FIFO. The first one is synchronous FIFO and the second one is asynchronous FIFO. The synchronous and asynchronous words are referring to their timing references. In synchronous FIFO, there is only one clock domain, whereas in asynchronous FIFO, there are two clock domains to do read and write operation. Due to the presence of two different clocks in asynchronous FIFO, there should be special care needed to avoid metastability and ensure safe data transfer between two domains. By special care, I mean gray code pointers and synchronizers are needed. No such care is needed in synchronous FIFO as there is only one clock domain for both read and write operations. So in this video, we will only discuss about synchronous FIFO, its design and verification using Verilog. And here comes the main agenda of this FIFO, synchronous FIFO. A synchronous FIFO is a type of data buffer used in digital system to store and retrieve data in the order it was received. Synchronous refers to the fact that read and write operations are controlled using the same clock signals. It ensures that data is written and read in lockstep with shared timing references. The read and write pointers are updated synchronously with the clock, particularly crucial in high-speed systems where timing violation can lead to data loss and data corruption. We use synchronous FIFO for simpler designs. Here is its key features and applications. Key features are same clock domain, order preservation, buffering, control signals. Answers and its applications are data buffering between producer-consumer process, communication interfaces, pipeline data processing systems. These are the specifications of FIFO I designed in this video. Specifications are like module name I used is sen underscore FIFO. Parameters is width and depth are 8 and 16. What depth means? Depth means capacity of the FIFO. Like how many elements it can store at a time. At a time, it can store 16 elements in total. And the width of each element could be 8. And the ports I used here are inputs as clock, reset, D in, write enable, read enable. Outputs are D out, full and empty. Full and empty are actually flags. When FIFO is full, the full flag should be high, otherwise it's low. Empty, when FIFO is empty, empty flag should be high, otherwise it is low. And registers are mem, write pointer, read pointer, and count. Count is actually what I use to count the number of elements in synchronous FIFO present at a time. This is this RTL code of synchronous FIFO we designed, whose width is 8 and depth is 16. So you can see for write operation we are using write pointer and for read operation we are using read pointer. Our pointer get incremented by 1 whenever we are writing something in our FIFO, and at that moment the count should also incremented by 1. Whenever we are reading something from our FIFO, the read pointer should get incremented by 1 and the count should get decremented by 1. In the last, if you zoom in the last, you can see full and empty condition. For full, the count should be equals to depth, that is 16. So when the count is equals to 16, we are having 16 elements in our FIFO, which is its capacity. So its capacity is basically full. At that moment, our full flag should be high, otherwise it should be low. And for empty, the count should be 0. It means our FIFO should be empty. There should be no element present in our FIFO for empty condition. So whenever there is no elements present in our FIFO, the empty condition is fulfilled and our empty flag should get high. Otherwise, it is low. So this is all we write in our RTL code. As we already done with the RTL code of our synchronous FIFO, whose width is 8 and depth is 16. So now we verify our design by writing our test bench code for all the possible scenarios we can think about. Now, starting from the reset check, we will do all other operations check. Like starting from reset check, then we will do write operation check, then read operation check. Then we will try to write something in our FIFO when FIFO is already full. Then also we try to read something from our FIFO when FIFO is empty. Then at last we will check for wraparound condition. So starting from reset check, how we will do reset check? We assert and deassert reset. When we assert reset, the pointer should get at 0 index and the FIFO should get empty. And the empty flag should get high at that time. The next is write operation check. Whenever we are trying to write something in our FIFO and the FIFO is not full, the FIFO should accept that data. And when the FIFO gets full, the full flag should get high. Then the third one is read operation. Whenever we are trying to read something from our FIFO after writing is done, the full flag should become low as the number of elements is decrementing right now as we are reading them. So in this way, we are doing read operation check whether it is working properly or not. For doing write in full FIFO check, when our FIFO is full, already full, and we are trying to write something in it, then the FIFO should not accept that data as its capacity is already limited and it's already full. The capacity of FIFO cannot be extended. So we have to check whether this scenario is working properly or not. Then the next one is we have to check for read in empty FIFO. When our FIFO is already empty and we are trying to read something from it, then the FIFO should not permit this. And when FIFO is empty, it has no data to read. So this is not permissible and we have to check for it, like whether for this condition the FIFO is working properly or not. Then the last one is wraparound condition. For wraparound condition, we have to check when our read pointer or write pointer is at the last position of our FIFO. Then for the other write and read operation, it should get again at the 0 index. So this is our first test case, that is reset check. When we are asserting reset in our FIFO, then the status flags that are full and empty are set correctly. As we can see, our FIFO is empty. Then the empty flag should get high and the full flag should get low. No unwanted read and write operation happen after reset until enable signals are activated. So we can clearly see that our FIFO is passing the test and it is working properly for reset operation. So the test status is checked for this test. Into our next test case, that is read from empty FIFO. Till now our FIFO is empty as we have not done any write operation in it. So it is containing no data. And when we are trying to read something from it, it should not give us any data as D out, even when our read enable signal is high. So let's check for it. In the waveform, you can clearly see that when read enable signal is getting high, we are not getting any data in D out. So our this test case is passed for the FIFO we designed. Moving to our third test case, that is simple write operation. We have to check whether our FIFO is working properly or not for our write operation, and our flags are working properly or not. So here in these waveforms, you can clearly see that we are writing values from 0 to 15, and after writing 15 value, our full flag is getting high. So by these waveforms, you can clearly see that our write operation is also working properly in FIFO. So this test is also passing. Now we have to check it for write in full FIFO condition. Till now our FIFO is already full as we have already written values from 0 to 15. So even if our write enable signal is high, it should not accept any value as D in. So let's check it in waveform. As we can clearly see, our write enable signal is high after 15 as D in, but it is not accepting any value as D in. So our FIFO is also passing this condition. Till now our FIFO is already full and we have to check it for write in full FIFO condition. Whether it is accepting value if it is already full. Now we have to check our FIFO for simple read operation. What we are doing here is the values we have already written in our FIFO, we have to check it for read operation. Whether those values are coming properly in our read operation or not as the out signal. So in these waveform, we can clearly see that the values we have already written from 0 to 15, and when we are trying to read it, those values are coming as it is in the same sequence in our D out signal. So through this, we can say that our simple read operation is also working properly. So here's come is the last test, that is wraparound condition test. What wraparound condition actually is? A wraparound condition occur when read or write pointer reaches the end of the memory and wraps back to the beginning, that is index 0. For example, here as you know the capacity is 16. So when the write pointer reaches index 15 and again we try to write something in it, but it will not accept as the FIFO is already full, then we try to read something from it. So after we have done our reading operation, the FIFO should accept our write operation from index 0, that is from the beginning of the memory. So let's see it, or let's understand this from waveform. So here we can see in our D in signal, first we write value from 0 to 15. Then we read some values. Then again when we are doing write operation, it is working properly. So this is what wraparound condition is. So through these waveform, we can say that our wraparound condition is also working properly in our FIFO. Till now, we have designed our synchronous FIFO and also verified it for different test scenarios. So now we can say that our synchronous FIFO is working properly. And to conclude this presentation, I would like to say that synchronous FIFO is not just a FIFO, it plays a very crucial role as buffer to provide a bridge that ensures seamless data flow between two modules. Thank you for your attention. Have a nice day.